So we are very happy to have Tom. He has joined us last summer, and he will tell us about generalization of generalized global symmetries and the swampland. Please start.
Great. Thanks a lot. And thank you very much for the invitation to speak today. Thank you all for coming. As you can see, my work here is going to be based on a couple of papers that are already out, and then a couple of papers which should be out in the very near future. So quick outline, I'm going to start out by very quickly going over the swampland. This is a topic I've discussed here a little bit in various seminars in the past, as well as in a little lecture series that I gave back at the beginning of the fall semester. I'm then going to talk about higher form global symmetries, what's called the completeness hypothesis, approximate global symmetries, and we'll connect this to the weak gravity conjecture, and I'll end with some conclusions. So to begin, the swampland, and really the whole idea of the swampland is nothing more than trying to discover and extract universal features of quantum gravities. And there are a number of such features which have at least been conjectured to be universally true in all quantum gravities. You see here just a small sampling of the complete list. Things like no global symmetries, which we'll talk about in some detail today, the weak gravity conjecture, a number of other conjectures. And sort of unfortunately, there's this famous trade-off when it comes to these conjectures. To be more rigorously established, perhaps some might even say proven, tend to have less interesting implications for phenomenology and cosmology, whereas the conjectures that tend to be more interesting tend to be less rigorously established. And indeed, I think it's very likely that at least some of the conjectures on this slide are not in fact true, at least not universally in quantum gravity, though they may hold in some limited regimes. So where we'd really like to be is up here in this upper right-hand corner, where we have rigorously established statements, which are also very interesting for phenomenological purposes. Now, a number of these different swampland conjectures are related through various connections. So here's just a part of the swampland web, if you will. Some statements can be related, say, weak gravity conjecture and its magnetic version, or rather simply related through electromagnetic duality. But then some other conjectures, which maybe don't seem to at least naively be related, can be related to through more complicated ideas, such as emergence. And I won't go into that in much detail here, but instead, what we'll do today is we'll see how many of these swampland conjectures can be related to a single one, which is the statement of no global symmetries in quantum gravity. So if you will, the goal for today is to try to introduce some new links into this larger swampland web. And in order to do that, the first thing we're going to do is learn about what are called higher form global symmetries, also known as generalized global symmetries, in this seminal paper by Gaiuto, Kapustin, Seiberg, and Willett. So the idea behind a Q-form global symmetry is that this is a global symmetry for which the charged operators live on manifolds of dimension Q. So the ordinary global symmetries that we know and love from our introductory classes in quantum field theory would correspond to the case of Q equals 0. The charged operators are local operators supported on points of space-time, so they're zero-dimensional. Global symmetry transformations in general form a group G, which can be either discrete or continuous. For an ordinary global symmetry, it can be either non-abelian or abelian. We're all, I think, rather familiar with examples of non-abelian flavor symmetries, for instance. But for a higher form global symmetry, Q greater than 0, G is necessarily abelian. Now, if G is continuous, then under some reasonable circumstances, we're going to have what's called a conserved Nether current, which is a D minus Q minus 1 form. And the statement that it is conserved means that this D minus Q minus 1 form is closed. D of J is equal to 0. Now, some of you may be more accustomed to thinking of this as a Q plus 1 form current, which is co-closed. If you prefer that convention, then every time you see a J in my talk, you should put a Hodge dual in front of it. So you should put a star in front of J in your mind. But today I'm going to follow the convention of these authors. We're going to call this a D minus Q minus 1 form current, so that an ordinary global symmetry, for instance, has a D minus 1 form current. Now, in the modern view of quantum field theory, these symmetry transformations are implemented by these operators, which I'm going to call symmetry generators. They're sometimes called charge operators. In certain contexts, they're called Gukov-Witten operators. And these operators are each labeled by an element of the group G, and they live on a manifold of dimension D minus Q minus 1. They satisfy a fusion law, which is given simply by group multiplication. So if I take two of these operators living on the same manifold M, labeled by different elements G and G prime, I can fuse them into a single operator, which lives on the same manifold and is labeled by G double prime, where G double prime is given by the group multiplication of G and G prime. These operators are topological. And this is really the hallmark of a global symmetry. The fact that we have these topological operators labeled by elements of the group that fuse according to the group law. So topological here means that if I take some operator and it lives on some manifold M, then what I can do is I can deform this manifold M into another manifold M prime. And as long as this is a nice, smooth, continuous process, and as long as I don't cross over any charged operators in the process, then any observables, that is to say, any correlation functions involving this operator are going to be equal to any correlation functions involving this operator. Now, in the case where G is equal to U1, which is what we'll be primarily interested in today, we can be a little bit more explicit, and we can write these operators as the integral over the manifold M of the another current J, where alpha here labels the element of U1. And the fact that these operators are topological is related here to the fact that J is conserved. So if J is not conserved, they won't be topological, and vice versa. Symmetries in quantum field theory are associated with word identities. And in the language of these operators, what the word identities tell us is that if we take some charged operator on some manifold of dimension Q, we surround this operator with a charge operator, a symmetry generator, associated with a sphere which surrounds this charged operator. This is going to be equal to the charged operator we started with times a representation of the group. So for an abelian symmetry like U1, this is just going to be a phase, which depends on the element of the group and the charge of V. Pictorially, what's happening here, we have this charged operator. We surround it with one of these symmetry generators. Because the symmetry generator is topological, we can shrink it to a point. And that won't affect any correlation function. So this observable is going to be the same as this observable. And if we keep shrinking, we can eventually just shrink it to a point. And the word identity tells us that when we do that, we're going to just pick up a phase times the operator we started with. Okay, so let's do a simple example to maybe gain a little bit of intuition. So this is an ordinary global symmetry. We have complex scalar field theory. Lagrangian looks like this. We have some complex scalar field. Maybe we have some potential, which depends only on the product, phi dagger phi. The symmetry transformation here is going to take phi and rotate it by a phase. It's a U1 transformation because we have a U1's worth of phases. Another current is going to be given by this expression here. The charged operator is the field phi itself. It's a local operator, so this is a zero form global symmetry. And the word identity says that if I take one of these charged operators, I surround it by a symmetry generator, which is an S3, assuming that we're working here in 4 dimensions. And if I surround it by this field by the symmetry generator, this is going to give me back the field I started with times this phase. So what's happening here is that this symmetry generator is implementing the symmetry transformation everywhere inside of this S3. And so as long as this field phi is inside the S3, it will rotate. And if it's not inside the S3, we won't pick up a phase. Yeah.
If you consider like the defect operator and consider some word identity, the thing changes.
So we're just about to get to an example where we have some defect operator, which is charged under one of these symmetry transformations. Yeah. Yep. So in fact, here you go. So U1 gauge theory. We here have this Lagrangian, just ordinary Maxwell theory. We have a actually not just one form global symmetry here, but actually two one-form global symmetries, an electric and a magnetic. Then other currents are given respectively by star F and F up to these constants. And their conservation follows simply from Maxwell's equations. So in the absence of any electrically charged particles, D of star F is equal to 0. In the absence of any magnetic monopoles, dF is equal to 0. The charged operators here are these defect operators, as I was just mentioning. So the operators charged under the electric one-form symmetry are Wilson lines, which indeed are supported on curves of dimension 1. And in 4 dimensions, the magnetic operators are these 't Hooft lines, which are again supported on manifolds of dimension 1. The word identity for one of these Wilson lines, say, tells us that if we take one of these Wilson lines, we surround it by a symmetry generator living on this S2, which is the integral of the another current star F over the S2. This is going to be equal to the Wilson line we started with times this phase, which, as you can see, depends on Q of the Wilson line, as well as this phase alpha of the symmetry generator. Now, okay, so we've talked about symmetries. Now let's talk about how these symmetries may be broken. And looking at the symmetry here, we see that we can add in to our Maxwell theory charged matter. So for simplicity, we'll just say that we add in some fermion. It could be a scalar, it's not important. We'll say that this fermion has charge n. So that n here is an integer. You remember that we had, before adding this fermion, we had this conserved another current. But now, in the presence of this fermion, this current is going to no longer be conserved because d of star f is no longer equal to 0. So the symmetry is broken in the presence of this charge n fermion. Related to this fact is the fact that the charge n Wilson line can end on the fermion. So we no longer need to consider a closed Wilson loop. When we have this charge n matter, the Wilson line of charge n can end on this local excitation of the fermion field. And as you can see here, this is important because it allows us to unlink the symmetry generator by sliding it off and down below the charge n fermion, or below the charge n Wilson line. And what this allows us to do is it allows us to compute a single correlation function in 2 different ways. So suppose that we have this correlation function. This is the sort of thing that shows up in the word identity. I'm taking a charged operator, I'm surrounding it with a symmetry generator. So if this is a valid symmetry transformation, then this operator here is topological, and I can shrink it to a point and pick up this phase. This is the statement of the word identity. On the other hand, because this Wilson line can end, I can also unlink the symmetry generator by sliding it off the Wilson line, and now I can shrink it to a point down here. And because this symmetry generator doesn't contain any charged operators, when I shrink it to a point, it just gives me the identity. So if I now equate the left-hand side and the right-hand side, you see that I need to impose the condition e to the I alpha n equals 1. In other words, e to the I alpha is an nth root of unity. And what this is telling me is that in the presence of this charge n matter, I no longer have a whole U1's worth of topological symmetry generators. The symmetry generators which do not satisfy, the operators which do not satisfy this condition are no longer topological. So they're no longer symmetry generators in the theory with the fermion. The only operators that remain topological are the ones associated with alphas that satisfy this expression. And what these are going to do is they're going to fill out a Zn's worth. of topological operators. In other words, the U1 one-form global symmetry has been explicitly broken in this theory down to a Zn subgroup. So at this point, maybe I'll just mention an important guiding principle, which will show up throughout the talk, which is that just as quantum gravity is not supposed to have any global symmetries, any ordinary global symmetries, it's not supposed to have any higher form global symmetries as well. And really, as far as I know, the first paper to make this argument in a very clever way was this paper of Harlow and Oguri back in 2018. And so at least within the context of ADS CFT, Harlow and Oguri argued that such P-form global symmetries should not exist in ADS quantum gravities. Now, there's a sort of a standard lore that says that this absence of higher form global symmetries is related to something called the completeness hypothesis. And the completeness hypothesis is another swampland conjecture due to Polchinski, 2004. And the statement is that whenever you have some gauge theory, which is coupled to quantum gravity, there should exist states in every representation of the gauge group. So note that this is not in any way satisfied in quantum field theory, right? I mean, I can just consider pure U1 gauge theory. It doesn't have any charged matter at all. That's a perfectly valid quantum field theory. But the claim of the completeness hypothesis is that that can't happen in quantum gravity. You can't just have a pure U1 gauge theory. Rather, you're going to have matter. You're going to have particles or states of some sort in every charge. Now, that's one standard lore. So, or there's sort of two. One is that there's no global symmetries, no higher form global symmetries in quantum gravity. Another bit of standard lore says that's is this completeness hypothesis. A third bit of standard lore holds that these first two bits are related. Namely, the absence of global symmetries is supposed to be related to the completeness hypothesis. And in many cases, it's this relationship indeed exists, and it's not too hard to see. In fact, so we sort of have an example already. We looked at pure U1 gauge theory, and we saw that it has this electric one-form global symmetry, so U1 symmetry. We also just saw that if I have charge and matter, then this is going to break this U1 down to a Zn subgroup. And this means that if I have states of every charge, so in particular, I have a state of charge 1, then this is going to be broken down to Z1, or in other words, it's just going to be broken completely, and so I get no electric one-form global symmetry. And so at least in this case, you see that there's this very nice one-to-one relationship between satisfying the completeness hypothesis, having states of every charge, and the absence of any electric one-form global symmetry. So you might be tempted to think that this should just be a general story, that these electric one-form global symmetries disappear exactly when the spectrum is complete. But the problem is that that just isn't the case. So one example is S3 gauge theory. So this is a non-abelian discrete group, the symmetric group on 3 elements. Pure S3 gauge theory has no matter in any representations of the gauge group, and yet it also does not have any one-form global symmetry. So this is a counterexample to this third bit of lore. Incomplete spectrum, yet no one-form global symmetry. Nonetheless, there is sort of a generalization, an extension of this bit of standard lore, which does hold here. There are no electric one-form global symmetry operators, which are topological codimension 2 operators associated with a symmetry. But there do exist some more general topological codimension 2 operators in pure S3 gauge theory. What do I mean by more general topological operators here? Well, remember, when we were looking at symmetry operators, these were topological operators, codimension 2, that satisfied a very particular fusion structure. Namely, if I take one of these, labeled by an element G, and I fuse it with another one of these guys, labeled by another element of the group G prime, this is equal to a third element, a third topological operator labeled by the element G times G prime. Now for these more general topological operators I'm speaking of here, these will satisfy a more general fusion algebra. If I fuse two of these guys, I'm not going to get just a third guy, but rather a sum over topological operators. And so the more general statement here, which actually is true, is that completeness of S3 gauge theory is in one-to-one correspondence with the absence of these more general topological codimension 2 operators, as is discussed in my paper with Zhuang Xiao, which actually is already out. Sorry for the old slide here. So in fact, this is even a special case of an even more general statement. So the general statement, which is true, is that the completeness of the spectrum, satisfying the completeness hypothesis, is equivalent to the absence of electric one-form global symmetries for a compact gauge group, for compact gauge theory, provided that this gauge group is connected. And it's also true for G gauge theory if G is a finite abelian group. So this covers most of the examples of gauge theories that you're used to. It covers Zn gauge theory, it covers U1, SUn, SU3 times SU2 times U1. All of these fall into this category. But the more general condition for when G is a compact but disconnected Lie group, like say O2, or a finite non-abelian group, like say S3 that we just looked at, now completeness of the spectrum is equivalent to the topological codimension 2 operators, also known as Gukov-Witten operators. So this revision of this third bit of lore relating the completeness hypothesis to the absence of global symmetries actually suggests another revision to the standard lore. We tend to believe, and many arguments have been given actually even in the last few months, regarding the absence of global symmetries in quantum gravity. But we now see that actually global symmetries are really just special cases of more general topological operators and the fusion algebras associated with them. So it's very natural to suggest that just as how quantum gravity doesn't have global symmetry operators, it also shouldn't have these more general topological operators. Now it's actually interesting that the proof of Harlow and Oguri does not immediately carry over to these more general topological operators. There are some important subtleties which actually render that proof invalid, or at least it's not obviously valid. So this is a very natural statement. As far as I know, it's true in quantum gravities, and yet it doesn't have a proof at this point. So this is a question that I think would be very interesting to try to study, to perhaps adapt some of these recent arguments against global symmetries in quantum gravity to this more general case. So this concludes sort of the first part that I wanted to mention, the relationship between topological operators and the completeness hypothesis. What I want to do next is generalize the notion of higher form global symmetries, and specifically the absence of these symmetries, in a different direction. So we just talked about topological operators, which we saw were sort of a generalization of global symmetries. Now we're going to talk about approximate global symmetries. There's much less in the literature on approximate global symmetries than there is on exact global symmetries, for the reason I think that these things are just harder to define. But from what we've said so far, there's at least sort of a heuristic idea, or heuristic definition that you might have of what exactly an approximate symmetry is. So we saw before that when we have an exact symmetry, we get these charge operators which are exactly topological. That is to say that if I deform them in any way, as long as I'm doing this in a smooth way, it's not going to affect any physical observables. With an approximate symmetry, we expect, therefore, that we're going to get almost topological charge operators. Operators which, if we deform them a little bit, are only going to slightly affect the correlation functions that they appear in. So we can make this a little bit more precise by looking at the word identity that we had before. So we have this word identity. We have a charged operator. We have a symmetry generator, which comes from integrating the Nether current over a sphere. And according to the word identity, this is going to be equal to the charged operator we started with times a phase. So that's the case if the symmetry is exact. But if the symmetry is approximate, we now expect that this phase is going to pick up some radial dependence. It's going to depend on the radius of this sphere. That is to say that I can no longer just deform the size of the sphere at will without affecting any correlation functions. So we can quantify all of this by considering the variation of this phase omega. Specifically, we're going to take the logarithmic derivative of omega with respect to radius and evaluate at some distance scale r naught, which is the radius of this sphere. We're then going to say that at this distance scale, the symmetry is exact if delta is exactly equal to 0, in which case the charge operators are topological. We're going to say that it's approximate if delta is much less than 1. And we're going to say that it's badly broken if delta is order 1 or larger. Pictorially, we're taking our symmetry generator, we're surrounding one of these charged operators, and then we're wiggling the symmetry generator and seeing how these correlation functions are modified. Okay, so let's do this again in a first warm-up example, the complex scalar field. We have our complex scalar. We're now going to add in this dimension 5 operator, which breaks the global symmetry. So you can easily see that this operator here is not going to respect the rotation symmetry of phi. Now in the we have another current, looks like this. We have a word identity, looks like this. The phase here, omega, will be independent of radius in the absence of this term. But in the presence of this term, we expect it to pick up some radial dependence. So we take the limit as alpha goes to 0. This just means that we're considering an infinitesimal symmetry transformation for simplicity. This allows us to expand this exponent, bring down a factor of I alpha times the integral of j. And we see now that the word identity and the violation of the word identity is going to be encoded in this correlation function, which we can expand in diagrammatic fashion like so. Now, if you look at this first term in the Feynman diagram expansion, you'll note that this guy does not have any instances of this vertex. Therefore, you might expect that this guy is not going to violate the global symmetry, and in fact, you'd be right. This thing is in fact what's responsible for implementing the word identity in the first place, in the theory with an exact global symmetry. But now, in the presence of this dimension 5 operator, we're going to pick up diagrams like this. And these guys are going to lead to a violation of the global symmetry. And we can estimate this violation. Here and throughout the rest of my talk, I'm going to be just throwing away all order 1 factors. So there's some order 1 number here associated with this guy. And then there's some order 1 number times r lambda to the -2 associated with this guy. Well, here these two factors of lambda, of 1 over lambda come from these two vertices. So we can then, given this expression, we can compute the logarithmic derivative. And what we find is an expression for delta that goes like 1 over r naught lambda squared. So at this point now, we can consider two different limits. In the limit that r naught is much larger than 1 over lambda, the denominator is very big, so delta is very small. And therefore, we say that we have an approximate global symmetry. On the other hand, when r naught is order 1 over lambda, or smaller, now this denominator is order 1, delta is order 1, and we say the symmetry is badly broken. Now, why do we go through this argument, this whole calculation? It's really more of a sanity check than anything else. So if you walked in here today, you hadn't heard me talk at all about these topological symmetry generators and all of this hubbub, and I've just shown you this Lagrangian in 4 dimensions. I ask you, does this theory have any global symmetries? You'd look at this and you'd say, well, in the absence of this higher dimension operator, this thing does have a U1 global symmetry, which rotates the field phi. And because this is a higher dimension operator, it's an irrelevant operator. At low energies, I expect that this thing can basically be neglected. And so at low energies, I'm going to get this emergent approximate global symmetry. But when I go up to energies of order the scale lambda, now all of a sudden I can no longer just ignore this term. And so I expect that at those energies, the symmetry is going to be badly broken. What we've seen here is just exactly that. At energies of order lambda, or equivalently distances of order 1 over lambda, the symmetry is badly broken. And at longer distances or lower energies, we have an approximate global symmetry. So at this point, I want to make a Swampland proposal. A statement that we've already seen is that there shouldn't be exact global symmetries in quantum gravity. What I want to do now is make this even stronger statement, which is that approximate global symmetries should also be forbidden. Namely, they must be badly broken within the context of effective field theory. And more precisely, since effective field theory fails at the Planck scale, what we're saying here is that approximate global symmetries should be broken at or below the Planck scale. So why is this true? Why should we expect that something like this should be the case? So I'm not going to give a proof by any means, but I'll give you a few moral arguments why you should maybe think something like this should be true. The first one is that the old argument against exact global symmetries in quantum gravity deals with the existence of stable Planck-sized black hole remnants. These things will exist if you have an exact global symmetry, and these things are generally believed to be problematic. There are arguments why this is the case. So if you want to avoid these, you can have global symmetries. If we have an approximate global symmetry, if we have an approximate global symmetry at the Planck scale, we may not get exactly stable black hole remnants, but we do expect to give some long-lived black hole resonances. And the better the symmetry is at the Planck scale, the longer these things will live. So it stands to reason, therefore, that we shouldn't expect approximate global symmetries for the same reason. Perhaps a better reason, a more convincing argument, is the fact that this matches our intuition, at least in simple examples. So for instance, with the complex scalar field, if I give you a Lagrangian like this, and I tell you that this is coupled to quantum gravity, you say, well, okay, I have this, these higher dimension operators. Once I turn on quantum gravity, I expect that these things will be Planck suppressed. I expect to get, a family of Planck suppressed higher dimension operators. And therefore, I expect the symmetry will be broken at around the Planck scale. And that's exactly what we just saw. If this energy lambda is order Planck or m Planck or smaller, then the symmetry will be badly broken below the Planck scale. Finally, maybe even the best reason why you think that something like this is on the right track is the fact that it seems to agree with a number of our favorite swampland conjectures. And today I'm mainly going to talk about one, which is just the weak gravity conjecture. So let's go back and look at symmetry breaking. So we have this Lagrangian, if you remember, in the case of the OneForm global symmetry. This is U1 Maxwell theory. We add in this fermion of charge n. It breaks the U1 global symmetry so that the current is no longer conserved. But here, it's interesting to look at a couple of examples, a couple of different limits. So in limit as g goes to 0, this term here will vanish. And indeed, the dynamics of the gauge field and the fermion will completely decouple, and a OneForm global symmetry will be restored. Likewise, if I take the mass of this fermion to infinity, then I can effectively ignore this term. I can integrate out the fermion. And once again, d of star f will go to 0 at energies well below the mass of the fermion. And so in both of these cases, we sort of get this OneForm approximate global symmetry, which is restored if either g goes to 0 or the mass of this guy goes to infinity. And this is closely related to the weak gravity conjecture. So the weak gravity conjecture, you may recall, places an upper bound on the ratio, a lower bound on the ratio of the gauge coupling G to the mass m of the fermion. So what this is telling me is that I can't take G goes to 0 with m fixed, or m goes to infinity with G fixed, without A, violating the weak gravity conjecture, and B, restoring this one-form global symmetry. So this is sort of already a hint that there's this relationship between the weak gravity conjecture and symmetry breaking. But we can make this a little bit more precise by doing a analysis similar to the one that we considered for the scalar field. So here we have this Lagrangian. In the absence of this fermion, we have a one-form global symmetry. The charged operators are the Wilson lines. The symmetry generators are the integral of the Noether current. We want to consider the limit as alpha goes to 0 of the phase omega. So for this, we are going to consider an infinitesimal symmetry transformation. We take the limit as alpha goes to 0. We can expand this exponential. And we see now that the symmetry breaking of this term, the symmetry breaking effects are going to be encoded in this 2-point function, the same way that they were for the case of the complex scalar that we saw earlier. Now, this correlation function looks, I would say, rather intimidating, certainly more intimidating than the correlation function of the complex scalar field that we had before. But it's helpful to think a little bit physically about what exactly is going on here. So this correlation function, which is telling us the modification of the word identity, features this Wilson line V, which we can think of as just some Wilson line, which we'll say runs through time at the origin of space. Such a defect can be thought of as this very heavy just sitting at the origin of space and traveling through time. Now, what we're doing here is we're surrounding this probe particle with a two-sphere at fixed time, and we're integrating the electric flux over that two-sphere. And this actually is something that you've seen many times before. This is actually high school physics. It's nothing but Gauss's law. So at least at a classical level, at a 0th order, all we're doing here is we're computing the electric flux through a sphere that encloses a charged particle. And we know from Gauss's law that this is equal, the integral of the electric flux is equal to the charge enclosed. And in particular, it doesn't depend on the shape of this object, right? This is the statement that the operator is topological. I can deform the sphere as I wish, and it's not going to affect the charge enclosed or the flux through the sphere. So here we see that these complicated topological operators are just related to Gauss's law. Now I can also write this in another way by integrating the derivative of the Coulomb potential over this two-sphere. And this is also going to be equal to the charge enclosed. Now, what happens in the theory if I add in the fermion? So I'm adding in an electron, essentially, to pure Maxwell theory. What this electron is going to do is it's going to modify this effective potential, and therefore it's going to modify this integral. The effective potential is going to gain some additional radial dependence, and therefore this integral will also become r-dependent, as will this charge enclosed. Now, this modification of the effective potential is not a high school physics computation, but it is a textbook quantum field theory computation. So if you go look at Peskin and Schroeder, pages 253 to 255, at least in my edition, you find this very nice treatment of the effective Coulomb potential in the presence of the theory with a fermion. So what happens here, we have this Fourier transform of the effective potential. And in the absence of this electron, if we're not considering the electron, we can just ignore this pi term, and this will give us just the Coulomb potential itself. But in the presence of the electron, we're going to get these corrections encoded in pi, which are the 1 pi, one particle irreducible loop corrections to the photon propagator from loops of the electron. And so these will modify the potential. You can massage the integral, as Peskin and Schroeder do, to bring it to this form here. And from here, it's helpful to consider two different limits once again. In the limit where m times r is much larger than 1, you can see that plugging in this 2m into the exponential here will give me this exponential suppression of e to the minus 2mr. So this is at distances that are very long compared to 1 over the mass of the electron. I get these exponentially suppressed corrections to the Coulomb potential. This is, by the way, what's called the Uhling potential here. Now, on the other hand, when I go to shorter distances, m of order 1 over r, now I plug in 2m into this exponential, and this thing is no longer exponentially suppressed. So instead, I'll get this logarithmic term here. And in fact, this log is nothing but the logarithmic running of the gauge coupling in the theory with the fermion. So this whole phenomenon is really nothing but the phenomenon of vacuum polarization. As Peskin and Schroeder discuss, at long distances, what's happening here is that this G here is the renormalized charge. So this G is the renormalized charge that we see in infinity, and any corrections to the Coulomb potential are very, very tiny. But as I go to shorter and shorter distances, I begin to penetrate the polarization cloud and see the bare charge. And as I begin to penetrate this polarization cloud, I get this logarithmic running of the gauge coupling, which is reflected here. All right, so let's bring this back now to the approximate symmetry breaking that we were talking about. Having computed the effective Coulomb potential, we can now compute this expression here. And taking this logarithmic derivative at the infinitesimal transformation, what we find is that this quantity delta is exponentially suppressed at long distances, as you would expect. Corrections to the Coulomb potential are exponentially small. At shorter distances of order 1 over m, this delta here is proportional to n squared g squared. So our Swampland proposal, if you will, was the statement that this quantity delta, which tells us how strong the symmetry breaking effects are, should be order 1 by the time we get to the Planck scale. So we get to very, very tiny distances of order L Planck, this should be order 1. And from this computation, this is telling us two things. One is that n squared g squared, the first thing is that the mass of this particle has to be smaller than the Planck mass. Because if it's larger than the Planck mass, then this term is going to be exponentially suppressed. The second thing it tells us is that n squared g squared has to be order 1. So if you plug those together, what you find is that n squared g squared over m squared has to be greater than 1 over m Planck squared, up to some order 1 factors, which again we're ignoring. And this here is really nothing but the statement of the weak gravity conjecture. The charge of the particle divided by its mass should be order 1 or larger in Planck units. Now, you might object for a couple of reasons to this. One of them, though, is you might say, it's kind of weird to have just a single particle. If this gauge coupling is very tiny at low energies, it's weird to imagine that you would have just a single particle of charge n that's very large, so that n squared g squared is order 1. Indeed, this is not the typical case in quantum gravity. In quantum gravity, when we have a tiny gauge coupling G, ordinarily what accompanies this is a large number of light particles. So let's suppose that we have instead this large number of light particles. What's going to happen, what this is going to do, first of all, is that it's going to bring down the energy scale at which gravity becomes strongly coupled. In other words, the energy scale at which effective field theory stops being valid. So this is what's sometimes called the species bound scale. It's the scale at which gravity becomes strongly coupled. And it's going to go like m Planck divided by the square root of the number of light species in 4 dimensions. Now, another thing we can do, so in this theory, if we have this large number of light species, is we can do the same computation that we just did to compute the symmetry breaking parameter delta. And it's the same computation. Now, instead of considering just a single particle running in loops, correcting the photon propagator, we're going to have many light particles running in loops, correcting this propagator. And each of them are going to contribute at an energy scale or at a distance scale R naught, provided that the mass is less than 1 over R naught. So we're just computing the 1 pi contributions from all of these different particles. We get this expression here, which can be rewritten in this way. And what we ultimately find is that if, in order for delta to be order 1 or larger at this species bound scale, we need for the average charge squared of these light particles divided by the cutoff lambda qg squared to be greater than 1 over m Planck squared. And since the mass of all these particles, by definition, is below the cutoff lambda qg, this is telling us that, in a sense, the average charge squared divided by the largest mass squared of these particles has to satisfy the weak gravity conjecture. So in other words, it's not like you have just a single particle which satisfies the weak gravity bound, but actually you have, in some sense, the average particle satisfies this bound. And this is very reminiscent of what's sometimes called the tower weak gravity conjecture or the sublattice weak gravity conjecture, which indeed holds that you shouldn't have just a single particle which satisfies the weak gravity bound, but actually you have sort of this tower of particles of increasing charge and increasing mass, which satisfy this inequality. So we're seeing here this close relationship between breaking the OneForm global symmetry at the quantum gravity scale and satisfying the tower weak gravity conjecture. Now, a couple of caveats here. You might ask, well, what about heavy particles? So as we saw, though, heavier particles give exponentially suppressed contributions to the breaking parameter, so they do not contribute significantly. And relatedly, we can integrate these things out to obtain some higher dimension operators. But these higher dimension operators will not actually break the global symmetry, though they may shift the definition of the current. So these higher dimension operators are not going to suffice to break this global symmetry. This is in contrast, if you remember, with the case of the scalar field. In the complex scalar field, we could add in this higher dimension operator to badly break the global symmetry. Here, in this case, that's no longer true. And this is related to the fact that the contributions to the symmetry breaking at very low energies were exponentially suppressed. Now, there's some other caveats here which are worth mentioning. My computations here today relied heavily on loop computations, and these will break down when we're dealing with weakly coupled strings instead of particles, which happens, for instance, in string theory. So it would be important to understand how these arguments may be modified in these cases. It should also be noted that there may be other ways to break the global symmetries. If we want to break the OneForm electric global symmetry, for instance, we do not necessarily need this whole tower of charged particles. We could just complete the U1 to a non-abelian gauge group. Now there's still going to be some global symmetry which is left over here. And so this sort of doesn't completely resolve the issue. But the point is that we, in this talk, have considered a particular way to break the global symmetries. And we've seen that this particular way gives us quantitative bounds, which are similar to the weak gravity conjecture. Now, another thing that's worth noting is that there are other versions of the weak gravity conjecture, which can also be related to the breaking of global symmetries by arguments similar to the one that we've considered here, a little bit more complicated, so we won't go into them today. You might also worry about the weak gravity conjecture at codimension 1 and codimension 2, but these are much more subtle. So what's the upshot here? We've seen that this slight modification of no global symmetries to the statement of no approximate global symmetries at the Planck scale has given us this relationship. We saw how this related to the weak gravity conjecture and the tower weak gravity conjecture, but it can be related to these other statements as well. So let me conclude here. Our goal for today, which we have hopefully accomplished, is to relate the statement of no global symmetries in quantum gravity to a number of other swampland statements. And we did this in two ways. First of all, we modified this from no global symmetries to just no topological operators whatsoever, which we saw is a generalization of the notion of a global symmetry. And we saw that this led us to this connection with the completeness hypothesis. We then generalized the notion of no global symmetries in a different direction, saying that we shouldn't have approximate global symmetries at the Planck scale either. And that led us to connections with these other conjectures. A number of lines of evidence or future research suggest themselves. Something that I think would be really nice would be to prove no topological operators conjecture in quantum gravity. Somehow finding a way to generalize some of the no global symmetries proofs that have been given recently. It would be nice to develop a more precise statement of this conjecture of no approximate global symmetries and to explain why it should be true. It would be nice to extend our analysis from approximate continuous global symmetries to approximate discrete global symmetries. In principle, conceptually, this is a trivial modification to what we've already done. Using our technology of these symmetry generators, seeing how their correlation functions are modified when we wiggle them, that perfectly is still a perfectly valid thing to do. But what's harder is the actual computations. So it's a little bit more practically involved to try to extend this to discrete global symmetries, but it would be nice to do so. It would be nice to apply these statements to other swampland conjectures. I think maybe the main takeaway lesson here is that we're seeing that these higher form global symmetries, which have played an increasingly important role in our understanding of quantum field theories over the last 5 or 6 years, play a very important role in our understanding of quantum gravities. And many of these statements, these swampland statements, things that seem to be universally true in quantum gravity, we now see that they sort of have a symmetry origin. So it'd be nice to see just how far these understanding these symmetries gets us in terms of understanding quantum gravity. And it'll be interesting also to try to apply these no global symmetry statements to phenomenology. There's some recent work. I have some recent work in these directions with my collaborators in this paper on what we call Chern-Weil global symmetries in a paper that came out in December of 2020. But I think there's still a lot of work to be done in thinking of how we may actually be able to get some phenomenological mileage out of this. So I'll stop at this point and thank you all for your attention.
Thank you, Tom. Questions?
Hi, Tom.
Hi.
Do you think for the approximate global symmetry, I can certainly buy that generic statement, but is it like a genericity involved here? I thought so, but for example, in your case of 5 to the 5th higher dimension operators, and coefficient should naturally be order 1 in Planck unit or cutoff unit, that I agree. But usually, like in some portion of the landscape, like 1% portion, and then coefficient could be 0.01, and 1,000 and small portion, and 10 to the minus 3. I don't have any argument to cue that. Namely, the statement of approximate symmetry is that suppression should not be stronger than what the naive measure or the measure in the landscape suggests. Are you saying that's stronger than that or not?
Well, yeah. So in that particular example, I just considered this dimension 5 operator, but actually, if you look at the argument, what you'll see is that it it doesn't need to be a dimension 5 operator. It could be dimension 6 or dimension 7 or right, or even 9. So this is sort of a problem for phenomenology, right? Because what you really want for phenomenology is to be able to bound things like you want to be able to bound dimension 5 operators or maybe dimension 6 operators. You don't really care so much about dimension 9 or 10. But where I think this becomes relevant in, at least as far as understanding the global symmetry breaking, is, you could imagine that, somewhere in the landscape, yes, the dimension 5 operator is sort of abnormally small, so that it's suppressed by a scale that's maybe a lot larger than the Planck scale. What I think would be very difficult is to sort of suppress all of the operators.
But all these things becoming important precisely at the limit that the energy scale goes to, right? So it's practically,
that's what
you can dump as fast as you want by suppressing coefficient from lower. Of course, it's just becoming more and more unlikely, as you said.
Yeah.
But okay, then I kind of agree that it's because then it's an almost statement that the exact global symmetry cannot be obtained because it's a measure 0.
Yeah. So that's why, this is where this is why I give this is sort of a sanity check on why you might think that the statement that global symmetry should be badly broken at the Planck scale should be true. In this example, it's sort of self-evident based on how we expect you're going to get Planck suppressed operators. That's exactly what you need. It's not making any sort of special statement in that particular example, but I think I think that this is maybe pointing us to something more general, which is that in general you shouldn't have good approximate global symmetries at the Planck scale. So then we can then what we see is that that's actually related to a number of these swampland conjectures.
Beyond the measure suppression.
Exactly.
So you mentioned the average version of weak gravity conjecture. Can you say something more about how the distribution of this setup, more than the average? Is it just?
Not from this argument, I don't think. Not from this argument, but so if you look at examples in string theory, right, sort of they have a distribution which isn't totally crazy, I guess, is the thing. So what you expect from the tower weak gravity conjecture is just a tower of particles of increasing mass and increasing charge. And as long as the charges, as long as the distribution isn't very, very, very heavily skewed towards small charge guys, what you'll find is that they indeed break this one-form global symmetry by this by this computation here, by an order 1 amount at the quantum gravity scale. So in practice, actually, what we tend to see is even the opposite. If you look at string states, when you go to larger charge, you get more and more states of that charge, rather than fewer. And so it's kind of hard to imagine, that you're gonna have a situation where you just have a ton of charge 1 particles, and then very, very few of charge order 10 and order 100 and order 1000. It's like the exact opposite of what we're accustomed to. So as long as something really bizarre like that doesn't happen, satisfying the tower weak gravity conjecture will correspond to breaking this global symmetry. So I think so the thing is, we can't really say too much about the distinct characteristics of the distribution, but this whole nice correspondence seems to work out, barring really weird distributions. Yeah.
I see. Can you tell a little more about why that the Harrow-Oguri argument doesn't apply to the more generic cases?
Yeah, that's a really good question. Let's see. Kind of hard to do without a picture if you're not familiar with the Harlow-Oguri argument already. Are you familiar with this argument?
Sort of, yeah.
Okay, so what they do, okay, so the way that this argument works is that they they essentially will split the symmetry generator U into a product over symmetry generators that apply only in some small region. So I'm gonna try to draw this here if that's okay. Okay, so let's see if I can. Okay, yeah, so there. So this outer circle here is the boundary. So this is where the CFT lives. This is a fixed time slice. Looking at it from above. So the CFT boundary is here of dimension D, and then the inside here is the bulk of dimension D plus 1. And so what they do, so they start out with a symmetry generator, which applies at the entire time. And they look at that. They look at how that translates to the boundary, and that's it. So it's a symmetry transformation on the boundary. And what they then do is split that symmetry generator on the boundary into a product over symmetry generators that apply only in a little region, so each of which only applies in a little region. So we're just taking the symmetry generator, we're splitting into a product of things that apply only in smaller regions. And then using entanglement wedge reconstruction, since this operator that applies in this region only acts right here, it's supposed to only, in the bulk, act on operators in the entanglement wedge of this region. So there's sort of a contradiction here that arises if I consider a bulk operator, a quasi-local bulk operator that's in the middle right here. If it's charged under the symmetry, then I can act with the symmetry generator and it will transform. On the other hand, what I can do is on the CFT, I can split that symmetry generator into a product of all of these guys, each of which acts only right here, which means that none of them are acting in this middle point. And so therefore, since none of these guys are acting on here, we should just pick up a phase of 1. It's almost exactly the same as where we had this unlinking diagram here. So you can compute it two different ways. One is that you can just implement the symmetry on the operator and you pick up this phase here. The other thing you can do is split the symmetry generator into a product over things in the CFT, and then you're sort of like unlinking the operator. Okay, so now where does this argument go? Where does it go south if we're dealing with topological operators instead of symmetry generators? The problem is this splitting procedure. So when you have these symmetry generators, a property of them, which is very nice, is that they can be split in this way. This is not the case with these topological operators. You're not allowed to sort of split them into a product of operators that act only in subregions. This is, you can, if you look at the last section of my paper with Xiuheng Xiao, we have a discussion of this in more detail, but basically this is the issue, is that you can't make that step of splitting, and then the whole entanglement wedge reconstruction argument just goes south.
I see. That's very clear. Thanks.
Yeah.
Other questions?
All right, shall we thank Tom again?